So start making a list of the different ways you can describe the differences in these right triangles. Just a couple minutes on this. Jack, good, are you here? Lauren Hudson? Oh, Jack Good is here. Go sit back there, Jack, because I'm recording the lesson, so I don't want the iPad to get messed up. Emily Post is Maddie is here. Maddie. I saw some. No. Okay. What are the different ways we can describe the differences in these triangles? What kind of differences do we see? Yeah, Alec.
Differences in angles.
Different angles, right? Good. Different angles. Yeah.
Different side lengths.
Different side lengths. Also good. Yeah. Mila?
Different areas.
Different areas, because they have different side lengths, they're going to have different areas, right? Okay. What else? Lauren, sit at one of the front tables today. Yeah?
Different hypotenuse.
Yeah, different hypotenuses, hypotenuse. Yeah. Okay. Different lengths of hypotenuse. Yeah. Okay. What else? Yeah?
Some are going to say different angles.
Yeah, different angles. Yeah. Yeah. We have that. Okay. What else? Yeah. Perimeter. Yeah, so overall perimeter is probably different. Side lengths are different, right? What's it called when... So these two have something in common compared to this, right? What's that called? So like orientation, right? Like for this one, the hypotenuse is angling this way, whereas these are angling that way. Right, the right angle is on the left side of the triangle on this one, or in this case on the right side, right? So you can like rotate triangles and flip them, and that's their orientation, right? And then last thing we can talk about is, yeah, if we have different side lengths, then we also have different ratios, right? Side ratios. So the ratio of one side to the other is going to be different compared to, are these three triangles. The ratio of the bottom side to the hypotenuse, right, is going to be different. So remember that these are called like the legs of the right triangle, and this is the hypotenuse, right? And there's a way to distinguish between the two legs. What do we call them? Do we call them leg 1 and leg 2? There's a way. There's a way in trig math that we use to describe them. Yeah. Well, yes, so sine, cosine, tangent is how we end up talking about the different ratios, right? But yeah, so let's start talking about that. Okay, so sine of theta is going to be the opposite to the hypotenuse, right? The ratio of the opposite to the hypotenuse. Cosine is the adjacent to the hypotenuse. Tangent is the opposite to the adjacent. Okay. How do you often remember this as like so ka toa, right? So ka toa. There's a lot of different memory tricks for remembering these ratios. Do what you got to do to know them, because they will keep coming up in physics and in calculus in the future. So make sure you have a good grasp of them. So in order to talk about side ratios and do math on side ratios, we just had to give them a name. So that's where sine, cosine, and tangent came from, right? Rather than just looking at one triangle and saying, well, these two triangles opposite the hypotenuse have this ratio, and this triangle has a ratio of opposite the hypotenuse of this. Okay, we just came up with a name for that ratio so that we could do math on that ratio. So sine ended up being opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite adjacent. Okay. What do I mean when I say opposite and adjacent? What is that in reference to? Yeah, Lauren.
The hypotenuse.
Not the
Or
hypotenuse.
the right.
Yeah, not the right angle. Okay, yeah. So not the right angle. Okay, the right angle forms the opposite of the adjacent, right? But this is adjacent means next to, right? And opposite obviously means opposite. So what is this opposite of? What is it opposite of?
Hypotenuse.
Not the hypotenuse, because this is also opposite. It's opposite the reference angle, which we just call theta.
Oh, it's
Yeah.
opposite of theta.
Yeah, opposite of theta. Good, yeah. Adjacent to theta, to this reference angle, right? So we have reference angles, and so the idea behind sine is that a reference angle of 30 is always going to produce a triangle that has the same ratio of opposite hypotenuse, no matter how big the triangle is. So here you can see a triangle and then a bigger triangle and an even bigger triangle. If you look at the reference angle of 30, 30, 30, okay, sine of 30 is going to produce the same value for all of these triangles. So opposite is A in this case, hypotenuse is B. So the ratio of A to B is going to be the same as the ratio from C to D, right? The opposite of the hypotenuse is always going to be the same value. And then it would also be the same ratio for this side length compared to that hypotenuse, right? So A over B should be the same numerical value as C over D. And then Lucas, remind me, why am I using A? Why am I using this side and not this side in this case?
Because that's the opposite.
Yeah.
That's what you use.
Yeah, so I'm using 30 as my reference angle, and we're using sine, so I need to do opposite over hypotenuse, right? So I picked the opposite side, which was A over B. And then for the middle sized triangle, it's C over D, because C is the opposite side of 30. Okay, or the opposite. Reference angle 30, okay? So you can try to quickly draw this picture, okay? Write down the ratio quantities, okay? And then always can go back through the lesson if you miss anything you need to add to your notes, okay? This picture will stay up too, so. Okay, so a certain reference angle of a right triangle always produces sides that are in the same ratio no matter how big the triangle is. So if I say that in this smaller triangle, the opposite side is 1/2, and the adjacent side is √3/2, and the hypotenuse is 1. All right, and now I want to figure out, well, what's that side and what's that side, given that its hypotenuse is 15, right? Well, then what would be this length? Hypotenuse is 15. Okay, let's think about it. So I have a ratio of 1 to 1/2, where this is the hypotenuse of the smaller triangle. And that's going to be equal to 15 over what? 7.5 or 15 halves, right? 15 over 15 halves. Okay? If I have 1 over √3/2, that's going to be equal to 15 over what?
√3/2.
Times what?
Times
15 √3/2, right? Okay? So they have to have the same ratios because they have the same angles. Okay? 15 √3/2 and 15 halves, right? And then what if we wanted to do the biggest triangle? What are we going to have? The biggest triangle has a hypotenuse of 23, so what's this going to be?
23/2.
23 halves, and this is going to be
23/3.
23 √3/2. Okay, good. Cool. So for review from last year, and in proof geometry, you learned that there's like these 30, 60, 90 triangles and 45, 45, 90 triangles that have special ratios, right? And you may have even memorized that like sine of 30 degrees is 1/2, or sine of 60 degrees is √3/2. You may have had that memorized. Okay, what we're going to do now is justify where these special ratios are coming from, just using some simple geometry, okay? So you can draw a You can draw a 60-60-60 triangle, right? Or you can draw a 30-60-90 triangle and then reflect it vertically and have another 30-60-90 triangle. And if you push those two triangles together, now you're going to have a 60-degree, 60-degree, 60-degree triangle. So what kind of triangle do we call that?
Yeah, equilateral.
Yeah, that's going to be an equilateral triangle, right? It's equilateral. Okay. So an equilateral triangle where I've already said that this is 1 and that's 1. So what's this? 1, right? But this equilateral triangle, if we split it right down the middle, we end up with these two 30-60-90 triangles, right? And what is the base of those 30-60-90 triangles then? It's 1/2 because we've just cut that right down the middle, right? So now we have that those two triangles have a base of 1/2. Okay, they have a base of 1/2, they have a hypotenuse of 1, right? And then what is the height? What is this value? Right? That's 1, that's 1, that's 1/2, that's 1/2. How do we find that?
X squared plus 25 squared equals 1.
Yeah, so what are you using there, Lucas? Do you know?
Something here.
The something theorem. There you go. That's that. No, I like that name. It's the something theorem. Oh yeah, so the Pythagorean theorem, right? Okay.
Yeah,
This is like the first, it might be the first thing you learn that has theorem attached to it when you're learning math. A squared plus B squared equals C squared, where C squared is the hypotenuse, right? So if you square the two legs and add them together, it's going to be equal to the hypotenuse squared, is what this is saying, right? So if we have one of the legs, we're not sure what this leg is, let's just call it y, or you can call it x. We can solve for that using Pythagorean theorem, right? So 1/2 squared plus x squared is going to be equal to 1 squared, right? So now we can solve for that height. Solve for that height just using basic algebra. What's 1/2 squared? 1/4. So we have 1/4 squared plus x squared equals 1. Okay, subtract 1/4 from both sides, you get x squared equals 3/4. And now you can take a square root of 3/4, which is going to be square root 3 divided by 2. Okay. So that root 3 over 2 number feels kind of weird, but this is where it comes from. This comes from taking an equilateral triangle with side lengths 1, cut it down the middle. What do you end up with? You end up with 1/2, 1, and root 3 over 2. Do you remember doing calculations involving square root 3 over 2 a lot last year? You did the trig values. It shows up on the unit circle a lot, right? Yeah. Am I good to move on? Okay, so now what we can say is sine of 60 degrees. Sine of 60 degrees, here's 60. Sine tells me what again? Sine is what ratio? Yeah, so sine of 60 is going to be root 3 over 2 divided by 1. This is the hypotenuse, it's just 1. Then sine of 60 is just root 3 over 2, right? If I do cosine 60 tells me adjacent over hypotenuse. So cosine 60 is 1/2 over 1, which is just 1/2. Okay. Which again tells me that if I have a triangle, or if I have a right triangle with a 60-degree reference angle, okay, and I know that the hypotenuse is 60, then what's the adjacent side have to be? It's got to be half of that. It's got to be 30. Right? If I change this and make it 111, this is going to have to be 55. Because cosine of 60 is 1/2, so the adjacent side compared to the hypotenuse has to be 1/2 if your reference angle is 60. Okay. Sine of 60 is root 3 over 2, cosine 60 is 1/2. Okay. All good? Sine of 30 is 1/2, cosine of 30 is root 3 over 2. So you notice these are just opposites of each other, right? So if sine of 60 is root 3 over 2 and cosine of 60 is 1/2,